So chemical kinetics is defined as the study of ways to make chemical reactions go faster or slower. So what we're going to do is look at reaction rates. So the reaction rate can be defined as the rate of a chemical reaction that's determined by monitoring the change in concentration of either reactants or products as a function of time. So this is very similar to your rates of change that you've done in either your math or HL class. So what we're going to do is reaction rates, they are usually obtained by measuring the rate at which a product is formed or the rate at which a reactant is consumed over a series of time intervals. We're going to calculate rate then as the change in concentration over the change in time. All right, so some examples of reaction rates. Our 10 liters of O2 is produced per second. Another example would be 0.50 moles of NO2 gas reacted per minute. 2.5 moles per liter of Ki reacted per minute, or 170 grams of NaCl produced per hour. Now, IB, most of reaction rates are done in units of moles per decimeter cubed per second. Okay, so you're going to see this in IB exams. So let's just take a quick look at a sample problem. We've got 144 grams of CO2 is produced by a reaction in 1 minute. It asks us to calculate the rate of reaction in terms of moles of CO2 produced per second. So the first thing that we want to do is convert our mass into moles. So we're going to do that as moles as mass over molar mass. We got 144 grams. Molar mass of CO2 is 44.01 grams per mole. So that is going to give us 3.2719 ... moles. Okay, so then our rate we're going to find as the moles per second. So we got 3.2719 moles of CO2 that is produced in 1 minute or 60 seconds. So that's going to give us a rate of 0.0545 moles per second. There are a few factors that will affect reaction rates. The first is the nature of the reactants. So chemical compounds can vary considerably in their chemical reactivities. So different reactants are going to react at different rates. The second factor that's going to affect reaction rates are concentration of reactants. So as the concentration of reactants increase, we have more reactants in the sample, so it's more likely that those reactant molecules are going to collide, and when they collide, they react. So that's going to increase our reaction rate. Our third one is temperature. At higher temperatures, reactant molecules have more kinetic energy. That means they move faster. That means they're going to collide more often and with greater energy. So they're going to, a higher temperature is also going to increase reaction rates. Finally, the last one, and biology folk will recognize this one, is our catalysts. So catalysts are going to change the rate of a reaction by changing the mechanism. We're going to go into this in more detail in a different video. Okay, so here's an example of a reaction that was studied to look for reaction rates. So we have chlorobutane reacting with water to form butan-1-ol and HCl. So what they did in this reaction is they measured the concentration of the chlorobutane at various times. So starting at time 0, we've got a concentration of 0.1 molar, and then as time progressed, all the way up to 10,000 seconds, we finally reach a concentration of 0 molar. So we can determine the rate for this reaction using the change in concentration of the chlorobutane divided by the change in time. So the average rate of the reaction over each interval can be calculated. So the way that this is done is if we're looking at 0, the interval between 0 and 50 seconds, we're going to take the change in the concentration between 0 and 50 seconds, so those are given here, divided by the change in time, and that's going to give us a rate of 1.9 times 10 to the minus 4 moles per decimeter cubed per second. So we can do that for each time interval. So the next one we would do is between 50 and 100. Okay. We would use those two concentrations and it'd give us this rate. So what you should notice is that as the reaction time increases, the average rate is decreasing. And that's because in the reaction, the reactants are getting used up, meaning that there are fewer collisions between the reacting molecules because there are less reactants. So as time goes on, the reaction rate is going to decrease. If we were to plot the concentration versus time for this reaction, it's going to give us a curve like this, shown here. So we can find either the average rate of change, or if we want to find an instantaneous rate of change, again, this is coming from math. We're going to take a tangent to our line and then find the slope of our tangent to that curve, and that's going to give us the instantaneous rate. So we can find it, say, at this point here, at time equals 600 seconds. Or we could find one at time equals 0, which is going to be your initial rate. So what you should notice is that the reaction is slowing down in time with time. So it's a very steep curve here, and the curve is less steep here. So the reaction slows down with time because the concentration of the reactant is decreasing. Now in this reaction, we have a 1-to-1 ratio of, if we're looking at the molar ratio of the chlorobutane and the butan-1-ol that's being formed. Okay, so they're reacting 1-to-1 ratio. That means that we can look at the rate of disappearance of this chlorobutane, but we could also look at the rate of appearance of this butan-1-ol. And because we have a 1-to-1 molar ratio, the rate of disappearance of the chlorobutane is going to be the same as the rate of the appearance of the butan-1-ol. The only thing that will be different is the sign in front. Because we're looking at the disappearance of the chlorobutane, it's going to have a negative rate. If we're looking at the appearance of the butan-1-ol, it's going to have a positive rate. So what happens then? Suppose that the mole ratio is not 1-to-1, as in this example here, where we've got hydrogen plus iodine reacting to give 2HI. Well, what it says is that 2 moles of HI gas is produced for each mole of hydrogen gas used. So the rate at which H2 disappears is only half of the rate at which the HI is generated. So we could write that as an equation, as an expression. So if we're looking at the rate of disappearance of H2, it would be the change in H2 concentration over the change in time. And that's going to be equal to half of the rate of the change in HI concentration over the change in time. All right, last thing, couple ways that we can measure reaction rates. So if you have a reaction that produces a gas, you could collect the gas and measure its volume and or its pressure as the reaction proceeds over time, and that would give you a rate. Another way that we could do it is if a reaction that involves ions and we had a conductivity apparatus, we could measure the conductivity over a period of time. And one other way is that if it changes color, then we can measure the intensity or the strength of color using a spectrophotometer. And we're actually going to do one of these labs later on in this unit.